Today's session in engineering communication will be focusing on presenting scientific information, in particular the various rules and conventions that need to be adhered to both in engineering and scientific report writing. Two terms that are often wrongly used and wrongly interchanged are accuracy and precision. In science, engineering and statistics, these two terms represent variability, but in a totally different way. Precision is the description of random errors, or what we often call statistical variation or statistical variability, as opposed to accuracy, which is a measure of the closeness of the result to the target or measured value. Take, for example, these two targets. Shooter A over here could be said to have quite good accuracy because most of the results are within the bullseye, but they have poor precision because the amount of variability is quite large. On the other hand, shooter B is missing the target for quite a bit, and shooter B could be said to have poor accuracy but at the same time good precision, or poor trueness but consistency in their results. We could say that B is consistently bad. Here we could improve on shooter A's results by having them hugging closer together, in which case shooter A will have both good accuracy and good precision. So we could have accuracy and precision, both or neither, depending on each situation. The variability in shooter B could be due to a whole range of random changes, changes in the wind velocity, changes or variations in the amount of explosive powder in the cartridge, or even the tension in their arms when they're firing. So in the case of A, we can at best only say that the shooter A has hit the target roughly 5 from the left and 4 up, whereas with B we could estimate the position a bit more precisely, such as 3.55 centimetres from the left and 2.55 centimetres up. So we can define this with greater precision and greater number of figures, which we're going to look at in terms of what we call significant figures. Have a look at this situation here. We have something that is 50 kilograms, but we measure it as 21.3456 with a great precision. The target or reference value over here is missed by quite a bit with that reading. So we say that we have very poor accuracy, but at the same time the amount of scatter in the results is quite low. Our precision is quite high. So we have situations where we could measure things very precisely with a great number of figures, but the answer is quite wrong or very inaccurate, and the significance of this is not really that important if the accuracy is way off. So this area of precision comes now into the realm of what we call significant figures. Significant figures mean exactly this. Take a situation where a certain town has a population of 52,000, where there could be a variation in several hundreds, whereas at the same time the population of the whole country could be 52 million. The 2,000 measurement is as significant in relation to the 52,000 population as the 2 million measurement is in relation to the 52 million. So in both cases there are only two significant figures in that result. The significance of the two in both cases is exactly the same. A bacterium may be measured with an electron microscope and found to have a size of 0.0002 millimeters. However, the resolution of this microscope may not allow us to determine whether the measurement is in fact 0.0023 or 0.0018. Relative to the measurement of 2, the amount of variation is even higher, and we have in fact only one significant figure, less significant figures for the bacterium measurement compared to the population of the town or country. So when we determine significant figures, there are certain rules. Rule number 1 is that all non-digit figures, all non-zero digits are significant. From 1 to 9, all digits are significant. Zeros appearing anywhere between non-zero digits, such as the 0 here or the 0 here, are significant because they have actually been measured. Leading zeros before significant digits are not significant. They are simply placeholders. So stating something that's 00052, these zeros are only placing the 5 and the 2 in the correct position of hundreds of thousands or tens of thousands, but they are not measured and therefore not significant. Trailing zeros after a decimal are, however, significant. For example, 12.2300, the last two zeros are significant because we have actually measured them. Otherwise, we would not have even stated them. Likewise, the 00 here are significant, whereas these zeros before the significant figures are not. These three zeros are placeholders only, whereas these have been recorded and therefore are measured and therefore are significant. Had they not been significant, had they not been measured, we would simply drop off the zeros after the decimal point. Zeros before a decimal point are not significant. So, for example, stating that something is 1,300, the 100 here is not significant because all we're saying is that it's roughly 1,300 or roughly 1,300. If we were to have actually measured it, we would state in brackets afterwards to 4 significant figures. The first thing we need to do is determine the number of significant figures the answer has to be recorded as, and once we've done that, determine the number of non-zero values to write down. If the digit after the non-zero value is greater than 5, we round the digit to the left up. If it's less than 5, we round it down. So, for example, if the measurement was 1.2459 and it had to be written to 3 significant figures, as in chopped after the 4, the figures after that are 5 and 9, so it's more than halfway and rounded up. If the digits afterwards were 3 or 4, it will be rounded down and kept at 1.24. Significant figures are more important in rounding than rounding to decimal places because it treats both large and small values equally. Take, for example, 12.345. Here it's been rounded to 6 significant figures, here to 6 decimal places, but as we start rounding it to less significant figures, notice the way that we truncate the value. Let's take, for example, the rounding to 3 significant figures. Rounding it to 3, it means that after that 1, 2, 3, the value after the 3, we have to determine to the right, is it above or below 5? Because it's 4, it will be kept at 3. And likewise, rounding 12 to 1 significant figure, we have to chop off the second one, and notice that the 2 is less than halfway, so 12 is closer to 10 than it would be to 20 or to 0. It is no different with small values. These values here, a decimal value, the rounding is exactly the same. We determine to what figure we are going to truncate or chop the value and look to the right and round down or round up accordingly. An interesting scenario happens here where the rounding actually affects the next position of the figure or the number. Take, for example, 9.96. If we had to round it to 2 significant figures, the 6 would round the 9 up to 10, but that 10 would then round the next 9 up to 10. So as a result, we get 10.0. And of course, rounding it to 1 significant figure, that 0 would drop, and the answer is simply 10. Now, the 10 is not 2 figures because that first 0 is really just a placeholder. When we have equations or formulae such as the equation for the area of a circle or for kinetic energy, the pi in this case and the half are considered to be precise to an infinite number of significant figures and does not affect the overall number of significant figures in our answer. So the rounding will not be affected by the half and the pi because it's considered to be infinitely precise. If we had this calculation to perform, noticing that the answer is 2.468, and we were asked to round it to the number of significant figures in the data, what we do, because it's a multiplication, is look at the part of the data or measurement that has the least number of significant figures. In this case it's 2, and round the overall answer to 2, hence it will be rounded to 2.45. When we are rounding to a certain number of decimal places, the rules are actually in reverse. We round it to the highest decimal place in the data or measurement. So it's the opposite rules to, or very different rules to, the rules for multiplication and division. Take, for example, 100.0 plus 1.2348. The number of decimal places in the leftmost figure is the first decimal place, so the overall answer has to be chopped off after the tenths, so it will be rounded to 101.2. To appreciate why we need to round to a certain number of significant figures, because there are variations or inaccuracies, lack of precision in part of the data. Take, for example, this calculation here. It's been based on the value in the denominator to be 4, and we get an answer to 7 significant figures, 2.1222275. But that 4 has been rounded to approximately 4. It could in fact have been 3.55 or 4.45. If it was 3.55, the answer would have been 2.391, 445, 1.907. Notice the amount of spread in those possible answers. Hence, that 1222 is really of no importance. It's actually ridiculous to record it because the variation can be actually quite high. When you're presenting results in engineering, we quite often have things measured with certain units, and each of these units may have a symbol to represent it. Take note of the way the symbol is written and write it correctly. Take note if it's uppercase or if it's lowercase. So if it's milligrams, we need to make the M lowercase and the G lowercase. Microfarads uses the Greek M or Greek mu. Notice that the mu has a tail on it, so it's not the same as the English U. So use the units correctly and take note of how they are written. Here we are looking at rainfall data for January and June in Adelaide or North Adelaide in 2016. This chart representing the data has the rainfall on the horizontal axis and the days of the month on the vertical. It in fact should be switched around because the days of the month are said to be independent, and the rainfall depends on the days of the month. Being the dependent variable, we need to record that on the vertical axis, so the axis should be switched around. The problem with this representation is also the fact that there's no labelling, and also there's no data points so that we know what the measurements are exactly meant to be. In the second case, we have a chart now that has correctly the days on the horizontal axis and the rainfall on the vertical. The data points are labelled now and indicated with squares or triangles. Notice that there's colour used here, but the fact that we've labelled some data points with squares and others with triangles facilitates black and white printing, because otherwise we wouldn't be able to tell which graph was which. So here, this representation is a lot better than the former one, and correctly placing the axes in the right order. The only issue with this, of course, is there's too much clutter. So when we are labelling axes, what we say is that label the major grid lines or major divisions, but indicate the minor ones with little notches, but don't actually add the numbers. Otherwise, you're going to have the axes too cluttered. There are a lot of ways in which we can represent data, and this chart here shows Napoleon's escapade or campaign, I should say, into Russia. Notice that the Mignard here has represented lots of information in different ways. There's dialogue up here. There's a legend indicating the distance of Napoleon's journey, and there are also different bands giving us extra information. This brown one indicating that the troops, or the number of troops in his army, noticing how many more soldiers there were at the start compared to the time when Napoleon reached Moscow. Florence Nightingale, a very well-known famous nurse and healer in the 1800s, developed what she called the rose diagram. The larger version of this rose diagram, in a very creative way, utilises size and colour to indicate different features. The big, or the large green wedges indicating preventable causes, or this is to show mortality rather, preventable causes being the significant one, the red one due to wounds, and the dark one, the dark black, indicating death due to other causes. So an interesting use of colour and shape. Ready now to consider dependent and independent variables a bit more closely. We call the independent variable, sometimes the cause variable, the one that we control and adjust, and this variable we usually represent on the horizontal or x-axis. The dependent variable, or the effect of changes in the cause variable, we represent on the y-axis or the vertical axis. It's important to understand which is the cause and which is the effect variable, and to label the axes accordingly. Take some of these situations in this table here. The road accidents are dependent on the amount of alcohol consumed, or we may find our exam results are dependent on study time. So the study time, the independent variable, would be labelled on the horizontal axis, whereas the results in our exam would be labelled or drawn on the vertical axis. When we take measurements or do calculations, we understand that there's always going to be some variation. It could be the variation in pressure we apply, the variation in temperature and humidity. So there's always going to be scatter in our results. And this is uncontrolled, as in to be expected. What we do look for, though, is correlation between our measurements. How are they connected? What is the connection between one variable and the other? For example, we may look at the correlation between heart attacks and smoking. We don't say that smoking creates heart attacks, because there's people who have heart attacks without having touched a cigarette, but we say that there's a relationship or correlation. How close that relationship is mapped is often measured by what we call a trend line, or sometimes called a line of best fit. If that trend line seems to follow a straight line, that trend line may then indicate what we call a linear relationship. In some situation, the relationship may be non-linear, and the trend line actually be a curve. Population growth would be an example. We know that population growth is exponential. So is the abilities of microchips to process information. It's growing exponentially, and the trend line would not be linear, but in fact would be a curve. So the line of best fit, or trend line, is measures how much scatter there are in our data points. The correlation coefficient indicates how close that trend line that we depict matches the pattern, and it's indicated by what we call an R value. In Microsoft Excel, though, Excel doesn't use what we call an R value, but uses a coefficient of determination, or R squared value, to depict the amount of scatter. So we can choose that when we are doing Excel by choosing the trend or regression type. Looking at this graph here, you can see the black squares indicating the data points, and they seem to follow a linear pattern or linear trend line. We know that the pattern is quite well depicted by that, because 0.901 is a value of R squared. We also notice in the data that there's a point over here, this red one, that we call a mask point or an outlier. Now this could be and this pattern, this is not following the pattern of all the other data points. And what we do with outliers is we tend to ignore it, don't try to include it in the trend line that we're trying to draw. The reason for this could be due to the fact that the reader or the person observing the instrument got bumped at that time, or the instrument got wobbled around, or even that the setting, the zero setting, could have been wrong. So outliers are data points that don't follow the trend of the remaining data and are often ignored. Looking at this graph here, we notice that the this is indicating the amount of paint deposited on a car body for a certain amount of time in a heated car booth, as well as the corrosion resistance. Notice that the time is the independent variable, whereas the amount of paint deposited is the dependent variable. Take note also that the major grid lines are marked and labelled, whereas the minor grid lines have divisions indicating their position but are not labelled to reduce clutter. The thing to note with this is the 0, 0, and one needs to always take note of the 0, 0 value in all measurements, especially in experimental data, because in the case of the amount of paint deposited when the body has not been in the paint booth at all for 0 time, has to be precisely 0. So 0, 0 is not just an approximation, but is a precisely defined point. So the line of best fit, or trend line, has to not just balance around the remaining points, having equal number or approximately equal number above or below the trend line, but has to actually go through 0, 0. Notice that the curve here, or the trend line representing rust resistance, is non-linear because the R squared value is highest. In fact, it's 1 for that relationship, so it's better depicted by a non-linear relationship than a linear one. But notice also it also goes to 0, 0. Why? Because without going into the heated car booth, there'll be no paint deposited and therefore no rust resistance. So determining the scale and your grid lines is important. Draw the graph large enough to be able to accurately or more clearly depict your data points, but try not to clutter it too much with too much labelling. Try to also make your major divisions multiples of 2s or 5s or 10, because otherwise you won't be able to work out the subdivision. For example, if this was 7, 14, 21 and someone had a reading of 5, you'll know that it would be between 0 and 7, but where exactly it would lie would be really hard to determine. So in this case here, it's easy to work out where 1 and 3 and in between values are because of the way that we've subdivided the axes. This comes to the conclusion of the delivery, but take note of a couple of other things. That in many engineering practices, companies have pro formas or standard calculation sheets that they require staff to use so they can set out their calculations in an ordered and consistent manner. So as much as possible, try to use these sort of calculation sheets whenever you're doing your work. At the end of this document that you are meant to also study in your take from the Moodle page, there are some exercises which we're going to do on significant figures and graphing. So what we're going to do is give you some, hand out the question sheets and get you to group up maybe with someone else and attempt them, and we'll look at them at the end of the session and see how much of what I've covered today has been understood. So thanks for your attention, and we'll commence with some exercises.